What is the main motivation behind the proposed self-critique pipeline in the paper?
The main motivation behind the proposed self-critique pipeline in the paper is to simultaneously enhance the mathematical and linguistic abilities of large language models, LLMs, for practical deployment. The pipeline aims to address the challenge of maintaining and improving both language and mathematical abilities in LLMs, especially in real-world applications where accurate mathematical reasoning is crucial. Unlike existing approaches that focus on either language or mathematical enhancement at the expense of the other, the self-critique pipeline seeks to achieve a win-win solution by integrating mathematical enhancement into the feedback learning period during LLM alignment. By utilizing a math critique model derived from the target LLM itself, the pipeline aims to provide judging feedback on the LLM's generated solutions, focusing on generating mathematically accurate and logically consistent responses. This approach eliminates the need for additional external supervisory models and manual annotations, making the training process more efficient and effective. Ultimately, the goal of the self-critique pipeline is to improve the overall performance of LLMs on mathematical problem-solving tasks while maintaining their general language capabilities, thus enhancing their practical utility in real-world scenarios.
How does the math critique model differ from traditional reward models in evaluating mathematical responses?
The math critique model differs from traditional reward models in evaluating mathematical responses by leveraging the contextual capabilities of language models to provide more accurate judgments through integrating reference answers. Unlike traditional reward models, math critique incorporates explanatory analysis along with scoring, inspired by the concept of thought chains, enhancing scoring accuracy and interpretability. Math critique classifies responses into 4 categories based on correctness levels, ranging from entirely incorrect to wholly correct, each aligned with specific scoring ranges. This model provides judging feedback on generated solutions by scoring responses between 1 and 10, based on predefined criteria and reference answers. In contrast, traditional reward models typically focus on reinforcing models based on external reward signals without the detailed analysis and interpretability provided by math critique.
Explain the 2 stages of the pipeline: rejective fine-tuning, RFT, and direct preference optimization, DPO.
The rejective fine-tuning (RFT) stage of the pipeline involves multiple sampling iterations where certain responses are rejected based on predefined criteria, while the remaining responses are used for supervised fine-tuning. A rejection sampling method based on math critique evaluations is implemented to refine the dataset, focusing on enhancing the LLM's ability to generate mathematically accurate and logically consistent responses. The dataset obtained from this stage is denoted as D_text RFT, where each question undergoes n samplings and the responses are evaluated based on math critique scores to ensure correctness. On the other hand, the direct preference optimization (DPO) stage updates the model directly by learning from a pair of correct-incorrect answers. After the RFT step, multiple samplings are done for challenging problems, and math critique is used to re-rank these samples and select the pair of answers with the most significant difference for learning. The dataset obtained from this stage is denoted as D_text DPO, where the chosen answer exceeds a correct bound threshold, while the rejected answer falls below a rejected bound threshold, ensuring the selection of the most appropriate responses for training.
What is the purpose of the MATHUSEREVAL benchmark dataset in the context of the paper?
The purpose of the MATHUSEREVAL benchmark dataset in the context of the paper is to evaluate the proficiency of large language models, LLMs, in solving complex mathematical problems in real-world scenarios. The dataset is designed to test LLMs on challenging mathematical questions that require advanced reasoning and problem-solving skills, including questions from high school level and above, as well as real-world application problems. Unlike existing academic math datasets, MATHUSEREVAL aims to provide a more diverse array of question styles and align more closely with practical user needs. It allows for the evaluation of LLMs' mathematical reasoning abilities under both GPT-4 Turbo and the math critique scoring methods. The dataset serves as a benchmark to assess the model's performance in open-ended mathematical questions and to compare it against other models across various difficulty levels and categories.
How does the proposed self-critique pipeline aim to enhance both mathematical and linguistic abilities of large language models, LLMs?
The proposed self-critique pipeline aims to enhance both mathematical and linguistic abilities of large language models, LLMs, by focusing on iterative training methods that leverage a math critique model. The pipeline consists of two stages: rejective fine-tuning, RFT, and direct preference optimization, DPO. In the RFT stage, the model undergoes multiple sampling iterations, where certain responses are rejected based on predefined criteria, and the remaining responses are utilized for supervised fine-tuning to enhance the LLM's ability to generate mathematically accurate and logically consistent responses. This stage refines the dataset by incorporating math critique evaluations to ensure the model's responses are correct and consistent. In the DPO stage, the model is updated by learning from a pair of correct-incorrect answers, with a focus on challenging problems that were difficult to resolve in the RFT phase. The math critique model is used to re-rank these samples and select the pair of answers with the most significant difference for learning. By iteratively training the model using math critique feedback in both stages, the self-critique pipeline aims to enhance the model's mathematical reasoning abilities while maintaining and improving its linguistic capabilities.
What are the key contributions of the paper in terms of methodology and results?
The key contributions of the paper in terms of methodology include the development of the self-critique pipeline, which simultaneously enhances mathematical and linguistic abilities of large language models, LLMs, through a two-stage process involving rejective fine-tuning, RFT, and direct preference optimization, DPO. The pipeline leverages a math critique model to provide judging feedback on generated solutions, focusing on improving mathematical accuracy and logical consistency. The methodology also introduces the MATHUSEREVAL benchmark, a test set designed for real-world scenarios requiring mathematical reasoning, and employs evaluation methods such as average score evaluation and hard split evaluation to assess model performance. In terms of results, the paper achieves state-of-the-art performance across various datasets, including MATHUSEREVAL, APE 210K, Math, and the language subset of AlignBench, surpassing similar-sized LLMs. The methodology significantly improves mathematical capabilities, particularly on open-ended math problems, and demonstrates competitive or superior performance compared to leading proprietary models like GPT-4 Preview. The study also validates the effectiveness of the math critique model in judging correctness and procedure accuracy, showcasing its superiority over previous models like GPT-3.5 Turbo. Additionally, the paper addresses limitations in handling graphic thinking and drawing abilities and precision calculation capabilities, providing insights for future work in integrating multimodal components and enhancing computational accuracy.
Describe the training process for the math critique model as outlined in the paper.
The training process for the math critique model involves constructing an accurate and robust evaluation model that scores mathematical responses generated by models based on questions and reference answers. The math critique model classifies responses into 4 categories based on correctness and methodology, with corresponding scoring ranges. The training data is collected by filtering a dataset from training data, including mathematics questions, reference answers, and model responses from various sources. The dataset is annotated using Critique, LLM, and ORM, generating a total of 10K annotated data entries. For responses in the middle range, A portion is manually annotated into 4 categories and mapped to a 10-point scale. The training process includes 2 evaluation methods: average score evaluation and hard split evaluation. The average score evaluation calculates the mean of critique scores for each model answer, while the hard split evaluation categorizes answers as passing or failing based on a correctness threshold. The math critique model is trained using the base model ChatGLM-3-32B with a learning rate of 3E6 and a batch size of 128. The training process involves multiple steps, including critique RFT training, which merges datasets from previous stages, and critique DPO training, which introduces a cross-entropy loss for the chosen answer to enhance stability. The DPO dataset is used for training, with a learning rate of 1E6 and training for 500 steps with a batch size of 64. The training process aims to improve the model's mathematical capabilities by providing accurate judgments on generated mathematical responses.
How does the paper address the challenge of maintaining and improving language and mathematical abilities in practical LLM deployment?
The paper addresses the challenge of maintaining and improving language and mathematical abilities in practical LLM deployment by introducing the self-critique pipeline. This pipeline focuses on enhancing both mathematical and linguistic abilities simultaneously during the feedback learning period of LLM alignment. It employs a math critique model derived from the target LLM itself to provide judging feedback on its generated solutions. The pipeline consists of 2 stages: rejective fine-tuning (RFT) and direct preference optimization (DPO). In the RFT stage, the model undergoes multiple sampling iterations, rejecting certain responses based on predefined criteria to refine the dataset and enhance the LLM's ability to generate mathematically accurate and logically consistent responses. In the DPO stage, the model directly learns from a pair of correct-incorrect answers, selecting the pair with the most significant difference for learning. Additionally, the paper introduces the MATHUSEREVAL benchmark to evaluate LLMs on real-world mathematical problems, providing a more challenging and practical assessment compared to existing academic math datasets. Overall, the self-critique pipeline aims to improve both language and mathematical abilities of LLMs without sacrificing one for the other, making it a win-win solution for practical LLM deployment.
What are the limitations and future work mentioned in the paper regarding the model's capabilities?
The limitations and future work mentioned in the paper regarding the model's capabilities include the following aspects. 1. Graphic thinking and drawing abilities. The model has deficiencies in handling questions that require drawing or graphic understanding. For instance, in a question from the Hungary test that involved connecting numbers, the model could list the topology but struggled to draw accurately. Future work may involve integrating multimodal components to address this limitation. 2. Precision calculation capability. The model may have deviations of up to 5% in computations involving multiplication, division, or exponentiation of 3 or more decimal places. This issue is common in pure language models and could be mitigated by using external tools for computation or integrating a code interpreter. Future work may explore solutions to improve precision calculation capabilities, possibly by incorporating external tools or code interpreters. These limitations highlight areas for improvement in the model's abilities, particularly in handling graphical tasks and enhancing precision in mathematical calculations. Future work may focus on addressing these challenges to further enhance the model's performance in real-world applications.
Explain the impact of data composition on the model's performance as discussed in the ablation study.
The impact of data composition on the model's performance, as discussed in the ablation study, is significant. The study revealed that using only academic datasets to construct rejective fine-tuning RFT data resulted in inferior performance in real-life scenario-based Matus-Rival and academic test sets compared to outcomes after integrating real-life scenario data. This indicates that incorporating real-life scenario data alongside academic datasets enhances the model's performance in practical, real-world applications. Additionally, introducing English data significantly improved performance on English datasets without substantially affecting Chinese capabilities. This suggests that diversifying the dataset with English data can improve the model's performance on English tasks without compromising its proficiency in Chinese. Furthermore, the ablation experiments during the direct preference optimization (DPO) phase showed that incorporating math-specific DPO data significantly enhanced the model's mathematical capabilities. This highlights the importance of including specialized mathematical data in the training process to boost the model's performance in mathematical reasoning tasks.